Hello, I'm Open's Heart. Welcome to episode 1 of my layman's series on climate. This episode will cover some basic parts of climate, more elemental parts than others might start with. I start here to help you understand climate and weather around the world. The goal is to explain how the existing system works and use that knowledge as a base, a foundation for the rest of our exploration on this subject. We will start with the water cycle. Many schools introduce the water cycle or hydrological cycle in their curriculum. It starts with water evaporating from the ocean, condensing and forming clouds, falling as rain. The rain feeds creeks and streams and lakes and rivers and eventually makes its way back into the ocean where it can evaporate and start the cycle all over again. So this is what they call the water cycle. Next, I'm going to introduce the water cycle's big brother. These are larger cycles that cover a lot more area. They have been called atmospheric cells. Here are the basic parts of an atmospheric cell. The sun hits the equator straight on, so this area warms up first and the most. As this area warms up, it warms the air above it. Now, one of the foundational principles of all weather and climate is that warm air rises. So as this air warms up, it rises. But it does not rise forever. It hits a boundary where it is much more difficult to rise higher. How can there be a boundary in the open sky? The answer has to do with the layers of the atmosphere. As you may have seen before, there are all these layers in the atmosphere. Air does not like to move between the layers, so the top of each layer acts like a ceiling, well, more like a top of a tent that can be pushed up a little bit, but not too far. Yes, things like a volcano can blast into the second layer or the stratosphere, but that takes a lot of doing. You can also see this principle working with thunderheads. The clouds will rise so high and then they flatten out. Sometimes the upper winds will spread the clouds in one direction only, so it looks kind of like an anvil. Other times it will spread out in various directions. This is what happens with our atmospheric cell. The warm air rises till it hits the top of the first layer, and then it can't go much higher. So it has to turn and spread out. In this case, the air moves north or south, away from the rising air of the equator. This air continues to travel a good long distance. As it travels, it will lose heat. Eventually, it will reach a point where it is cool enough to sink back down to the earth. When it hits the earth, it again has to change direction. It starts heading back to the equator, where it is warmed up and starts the cycle again. This gives us our first set of atmospheric cells, one on each side of the equator. Both cells start at the equator where warm air rises. The air rises until it hits the top of the troposphere, where it travels north or south until it cools and falls back to Earth. Then the air travels back to the equator. Notice where the air is rising or leaving, the air pressure is lower. And where the air falls, it piles up on the ground and the air pressure is higher. Air likes to move from high pressure to low pressure. So the difference between the rising zone and the falling zone helps to pull the falling air back to the equator. This strengthens the cycle and helps it to remain stable. These first two cells are called Hadley cells in honor of George Hadley, who contributed to this theory. Now let's see another view of these cells on a planet. Here we have a sideways view of our planet with the same Hadley cells and the same warm air rising at the equator. Now we're going to add another component. This warm rising air is warm, rising, wet, moist air, air with plenty of water in it. As the air rises, the water will condense into clouds and then rain. Thus, the area below it is going to get a lot of rain. This is where we find our tropical rainforests. This is why we have tropical rainforests. Once the air hits the top of the troposphere, it spreads out. As it travels, it will cool and lose water. By the time it falls, it has lost most of its water. It is dry air falling. This falling air zone does not get much rain. It tends to be an arid zone. Now, as the dry air falls, it piles up and gets compressed. Compressing the air heats the air. Thus, the people in the area will refer to it as a dry heat. So, we have tropical rain here, hot and dry here. You can start to see why we have climatic bands on the Earth. Let us move on to the next slide, where we can see how these climatic bands start to play out. Here is our tropical rainforest along the equator. To the north and to the south, we have an arid band. This arid band is not exactly straight across the planet, but you get the idea. To explain these other bands, we will have to add additional atmospheric cells. As the planet receives more energy, the energy is captured in these first two cells, as if it were filling up these first two tubs. If you add enough energy to the system, these first two tubs are going to fill up to overflowing, like a fountain that fills up the top pool and then it overflows, cascades down into a second pool, which becomes a second set of cells. This second set of cells are known as Farrell cells, in honor of William Farrell, who improved upon Hadley's theory. The Farrell cells start with downward falling air alongside the Hadley cell, only this time the air turns and moves north some distance until it rises, then it hits the top boundary and returns back south. Thus, the Farrell cell is turning in the opposite direction from the Hadley cell. These cells are like gears that have to mesh together. Where they meet, they have to be going the same way, which means each gear is turning the opposite way. Here, the motion of both is down, and then they both spread out, turning away from each other. Then they rise at the far side and turn back towards each other. This same gear effect holds true with the two Hadley cells. They both rise here, turn away from each other, fall on the far side, and then turn back towards each other. Thus, all these cells act like interlocking gears. If you continue to add energy, the second set of tubs will spill over into a third set, which becomes a third cell. In this drawing, the third cell is named the reverse Hadley cell. In other places, you will see it called the polar cell. Notice the interlocking gear effect is true of the third cell as well. This one starts with rising air alongside the Farrell cell, hits the ceiling and moves north until it cools off enough to fall at the pole. Thus, you have three cells from equator to pole. This is our primary rainy zone with wet, warm air rising. This is our primary arid zone with dry air falling. This is our secondary rainy zone with moist air rising. This is the temperate zone where many of us live, with rainstorms occurring on a periodic basis. Then this is our secondary arid zone with dry air falling. Wait a minute, you say, how can the poles be dry? Isn't there a lot of snow and ice there? It really doesn't snow that much at the poles. We get more snow here in the northern part of the temperate zone than the poles gets. It's just that historically, what did fall at the poles never melted. It just piled up. Thus, the poles are labeled as arid zones. You can think of them as frozen deserts. Thus, we have our 4 climatic bands: rainy zone, dry zone, rainy zone, dry zone, and 3 cells. Now, let's take another look at this. Here we have our 3 cells, only with additional features. Notice how straight these lines are, compared to how wavy this line is. Also notice the polar cell looks a little funny. We will talk more about these in the next episode, but for now, just notice the differences. Next, notice these arrows. These are surface winds. They are actually the bottom side of our cells, only they're not going straight as one might expect. That's because the Earth is spinning, which means the winds get bent. Instead of going straight north or south, they end up moving at an angle. That is why all of these arrows are diagonal. Notice how they are going away from the places where air is falling and towards places where air is rising. Let's take another global view. Here is a bit of a 3-dimensional view. We have the same cells and the same bent arrows, only this time they're labeled. We have the polar easterlies, the westerlies, the northeast trade winds, the southeast trade winds. These are the trade winds of the Earth, and the trade winds come from these cells. The cells and the direction of the cells are responsible for the trade winds. Trade winds are the prevailing winds that generally blow in the same direction. The trade winds affect how storms move. Here in the temperate zone, our storms usually come from the southwest and move to the northeast. In other parts of the world, storms may move in other directions. I would like to insert some of my own thoughts and ideas about hurricanes. As I understand it, hurricanes do not usually form down here in this convergence zone along the equator. Nor do hurricanes usually form up here. At least it's pretty rare for them to form up here. They normally form in the middle of this cell, in the Atlantic or the Southern Caribbean. The trade winds here are going west to southwest, so the hurricanes in this area are almost always moving west. The hurricanes themselves seem to want to get up towards the North Pole, so they want to move north. But they don't move north very fast here, and I wonder if that has something to do with the trade winds wanting to actually blow them south. It's sort of maybe they're fighting the trade winds. Then when they get to this area of falling air in between the trade winds, there usually is talk of uncertainty. The steering currents are weak or things like that until it gets through this area and it gets a little bit farther. And then the models and the things sort of can do a better job. And it usually continues moving the same direction for a little while. And then all of a sudden it turns or it curves. You see this over and over again where it curves because I think it gets caught in either the jet stream blowing this way, which is a whole nother subject we're not talking about here, or these prevailing westerlies. So you can kind of see the trade winds and the cell behavior in the paths of these hurricanes. This concludes this episode of our layman's story. We covered atmospheric cells, climate zones, and trade winds that drive our planet's climate, a climate that has been stable for 10,000 years. How much do we value such long-term stability? I invite you all to stay tuned to episode 2, where we build on this information to describe other climates a planet could have, from the coldest planet to the hottest planet.